All right, so let's get started. So welcome to our seminar to the CIE Bay Area chapter. CIE has a rich history dating back to 1917 when it was founded at Cornell University. Over the years, we've expanded across the United States with chapters in New York, Dallas, Seattle, New Mexico, Southern California, and of course here, the Bay Area. Our chapter, established in 1979, has been a pillar of the engineer community in this region for like 4 decades. So we got lots of entertainments right here, lots of memberships. And we got our sponsors right here. So at the core of our chapter's mission are 5 key values that drives our activities and initiatives. Our honors and build upon our rich cultures and professional legacy. We stay at the forefront of technological advancement. We nurtured and support emerging talents in the field. Our strength lies in the dedication of our volunteers members. We promote a harmonious blend of cultural diversity and professional excellence. These values guide us in bringing positive impacts to the Taiwanese and Chinese Americans engineering community. So our Bay Area chapter is home to several specialized technical groups. Each focus on cutting edge area of engineering, like the ET groups, EECS group, ETD group, EE group, and also Young CIE group. These groups provide platforms for knowledge sharing, networking, and professional developments in their respective fields. Now, I'd like to introduce our distinguished speaker, Dr. William Kao. Dr. Kao credentials are impressive. He holds BSEE, MSEE, also PhD as well, from University of Illinois Urbana-Champaign. His 30 years career spans roles at TI, Xerox, and Cadence. He has published over 40 technical papers and holds 8 patents. As a former professor at UCLA, he taught computer-aided IC design. Dr. Kao is a senior member at IEEE, and a founding member of IEEE Circus and System Silicon Valley chapter. And currently recently he also teaches emerging technology courses at UC Santa Cruz and Silicon Valley Extension. He has delivered over 19 seminars on various cutting-edge technologies. Dr. Kao truly embodies the spirit of lifelong learning and teaching in technology. Now let's welcome Dr. William Kao. Full screen. Okay.
Thank you, Ishi, for the introduction. Welcome to tonight's seminar. Tonight's seminar is going to be on a pretty new topic called Neuromorphic Computing, the next evolution in artificial intelligence. Okay, very good. Thank you. Okay, so for tonight's presentation, this is the agenda. This presentation is going to be an overview of neuromorphic computing. So by overview, I mean, I'm going to cover the 9 R's. What is neurocomputing? Why do we need neurocomputing? How does neurocomputing work? A historical development of NC, a couple of big vendors or companies working on NC, applications of neurocomputing, and then talk about the challenges and applications of neurocomputing. And then I'll conclude with a summary and conclusion. So just to start from the beginning, neuromorphic, the term neuromorphic is made up of two parts. The word is neuromorphic. Neuro stands for neurons. Neurons is the nerve cells, the cells that we have in our nervous systems as well as cells in our brain. Okay, so they're called neurons. So therefore the word neuron. Morphic itself, it means in the form of. Okay, so this technology is basically trying to mimic the way that the brain functions. So the brain is made up of neurons and allows synapses, the connections between the neurons. So this technology is trying to imitate the way that the human brain works, and therefore the word neuromorphic. So the reason why that's where the direction for AI right now is going toward is because currently there's still a lot of limitations for AI. For instance, it consumes a lot of energy, it is still relatively slow, and AI is trying to imitate the human in terms of how humans learn and adapt to new things. So the humans, we adapt to things very easily. So by adopting this neuromorphic approach, they're trying to make the machines imitate the humans and make the machines also more adaptable to the environment. Okay, so there are many tasks such as pattern recognition, sensory processing, and autonomous decision making. So everybody heard about autonomous driving, and so on. Okay, so we'll talk about all of that this evening. So again, just to introduce the topic, is it tries to mimic the human brain, not only in terms of the human brain structure, but also the way that the brain works, how the neurons interact with each other through synapses. Okay, and by doing that, hopefully the machines or the AI will be able to adapt just like humans do to environment. Okay, it can help us in the decision making. Okay, be able to learn new things, be able to reason, be able to plan, and navigate the complex environments that are continuously changing. So we'll talk about several applications that people are aware in terms of the AI, like self-driving cars, applications for elder care, and even outer space. Okay. Robots. Okay, so this is the next segment. I'm going to start by saying, what is neurocomputing? Okay, neuromorphic computing. What are the characteristics for this technology? And also the why. Why do we need it? So I'm going to start with the what and the why, and then I'll move on to how. Okay. So as I mentioned, this approach is trying to imitate the way that the human brain functions. So let's review a little bit about how does the human brain work. Okay. So inside our brain, the brain is made up of nerve cells called neurons. Okay, so here's a picture about how a typical neuron is formed. It has a cell core called the soma, and it has also two things. It has dendrites, which is the ones that receive signals. Okay, and then you have axon. The axon is how you send the signal. So basically, the way that the neurons communicate with each other is that one neuron sends a signal or a stimulus, and then the next neuron picks up the signal. So in the human brain, okay, right now there's about 10 to the fifth power, the number of neurons per centimeter square. There's actually about 100 billion neurons in the human brain. So we'll go over all of that stuff. And then there's quadrillions of synapses, because between neurons, there's interaction. For each neuron, there are maybe up to 1,000 interactions with other cells, brain cells. Okay, so you have almost a quadrillion, which is 10 to the 19 connections between neurons. Okay. So if you look at the bottom part of the slide, on the left side, you have the human biological, what we call biological brain. And then on the right side, we have artificial brain, which is the AI, right? So if you look at the things, is that we'll go over exactly how does the neurons work and interact with each other. And then we'll draw the parallel between the artificial brain, okay? And that's the AI, okay? So you have the biological brain on the left side and the analogous AI brain or artificial brain on the right side. And we'll try to see how they mimic each other. Okay, how does the AI mimic the human brain? Okay, so there are two components in the brain. One is, as I call, the neurons. The neurons are the nervous cells. It's not only the cells that make up the brain, but also throughout our body, we have neurons. Neurons means the whole nervous systems. Okay, you have all the nervous system throughout our body. Whenever we feel something, that's because of a nervous system. Okay, so we mentioned that the neuron is made up of the body itself, which is the soma. Okay, and then you have dendrites are the ones that where you receive the signal. Okay, the axon is where you send out the signal. Okay, and as I said, there are several kinds of neurons throughout our body. We have the sensory neurons, the motor neurons, because whenever our brain sends a signal to our hand or to our feet to move, for example, you have a motor function. Okay, when you send a signal, okay, move your left hand, right? So that's a motor neuron. And then you have the brain neuron, which is this. Whenever we feel something, for instance, we pick up a cup, okay, and let's say it's hot. You're feeling the sensor, okay. You sense the temperature, for example. So we have neurons, and the brain is made up of billions of neurons. Okay, so you can almost visualize the neuron. The neuron is almost like an atom. Okay, it's the most basic component of the brain. Okay, and then the way, so this is like a picture, you know, of how it looks like. So you have the center of the body is called the soma. Okay, and then you have these like arms and legs that feel it. Okay, so that's called dendrites. Dendrites are the receiving, the mechanism that receive the signal. Okay, and then the one that sends out the signal is called the axon. Okay, now, so between one neuron and another neuron, one sends out the signal, the other neuron picks up the signal, and it's all done through a stimulus. Okay, and that's why it's called synapse. Okay, so the synapses are the things that are between the neurons. So there's sort of like a chemical interaction that happens. Okay, and so one is the neuron that sends a signal, and the other one, there may be many receiving neurons that receives the signal or the stimulus. So that's the way they interact. Okay, so very important thing is a stimulus driven. Okay, and we'll talk about a little bit more about it. So if you look at the whole brain, so we're trying to do AI, we're trying to imitate the brain, right? So there are about 100 billion neurons in the brain. Okay, I guess the number is very hard to say how many. Okay, it may change also from person to person, right? And then you have about 80 to 100 billion neurons in the brain. And each neuron can have close to 1,000 interactions with other neurons. So those are done we call synapse. I don't know how to pronounce it. There's I used to work for Cadence Design System, so there's a computer called synapses. This is a little bit like that pronunciation. So if you multiply 100 billion neurons multiplied by 1,000 interactions, that's 10 to the 15. Okay, I don't know, for people who are like scientists and engineers, we're familiar with what we call scientific notation. Okay, 10 to the power of 15. Okay, so just for reference, when we talk about 1 million, 1 million is 10 to the 6. Okay, 1 billion is 10 to the 9. So the number of interactions is 10 to the 15, which is like 6 orders of magnitude larger than 1 billion. Okay, so it's a very complex system. It's also very small. So think about at the atomic and molecular level, right? So all of these things are very small. They are human cells are very small. That's the most basic component in the body. Okay, so let's draw the parallel between the biological brain and the artificial brain. So I guess on part A is the biological. So it's made up of the neuron with the dendrites and the axon and so on. Now, how do you represent that in artificial intelligence? Okay, so way back in the 1950s, they came up with a model, mathematical model called the perceptron. Okay, the perceptron, it basically has many inputs, a number of inputs, x1 through xn. Each of the signals are weighted. Okay, that means that you put a weight, different type of weights. Okay, so W1 through Wn multiplied by the input signal, and then you sum it all together. Okay, and then you come out with the output. And at the output, you also apply a filter. So on the input side, you take the input signal multiplied by a weight, you sum it all together, and then you apply a filter at the output, and then it goes out as the output. Okay. So we mentioned that in the biological model, you have neurons interacting with each other, and in the mathematical or AI world is represented by graphs, okay, quite called neural networks. Okay, so neural networks, this is a neural network. It's made up of nodes, and then you have also signals going in and coming out. Okay, and then when we talk about AI, we mentioned about deep learning. Deep learning, that means that from the input layer to the output layer, there are many layers. That's what it's called, deep layer. Okay, deep learning means that usually there are more than 10 layers, usually hundreds of layers, okay, depending on the size. So here on the left side, you have the biological brain and how it works. And then on the right side, you have the mathematical representation and how it works in the AI world. Okay. So that's what NC, neuromorphic computing, is. Now we come up to the next question. Why do we need neuromorphic computing? Okay. And the reason is because up to now, the architecture of the computer is based on what we call the von Neumann architecture. Okay, we'll talk about what is the von Neumann and what is the new neuromorphic computing architecture, how they differ with each other. Okay, but the traditional computing model, which is the von Neumann architecture, it has some basically flaws. Okay, first of all, it's very low energy efficient. Okay, it also has a latency issue. What does latency mean? Latency is just the response time. So when you send a signal and the time it takes to get a response, that's called latency. Okay, so very often, for instance, when we talk about the cloud means that the computer power is way in the cloud. That means it's very far. It's in a data server somewhere, owned by Amazon or Google or whatever, right? So if it's very far, when you send a request, the time that it takes for the server to pick up the request and then get back to you, that's the latency time. So latency time, usually if it's in the cloud, very long times, very long latency. And the problem is that right now, all the technologies that we need are real time. For instance, if you want to have a driverless car, the car needs to stop right on the dot, right? For instance, if the car senses that there's a pedestrian coming down and you need to stop, you cannot wait to send a signal to the cloud, wait for the signal to come back, because by that time, the person has already been run over, right? So what you need to have is you need low latency, and that's called real-time response. The other thing is scalability. What does scalability mean? Scalability means you can grow it to very large size or you can shrink it into very small size. Okay, that means scalable. It's sort of like a plastic thing. Sometimes it can grow very large, sometimes it can grow very small. Okay. Huh? Right. It's flexible. It's also changes, the size can change. Okay, that's scalability. So those are the problems that the current computers, the von Neumann architecture has. And what NC or neurocomputing provides is a cure to many of these problems. It's much more energy efficient. Response time is fast, low latency times, and it's scalable. Okay, so it overrides many of the limitations of the traditional computing. Okay, we'll get into a little bit more. So this is the next segment. I'm going to explain the difference between the von Neumann versus the NC. Okay, so if you just look at the bottom of this picture, one of the problems with von Neumann architecture is that in the computer, you have the processing unit. That means that the part of the computer that does the calculation, that's the processing. That's called the CPU, right? And then at the same time, you have also memory. So in a von Neumann architecture, those are separate. The CPU is sitting on itself, and then the memory is on the other one. So what the problem with that is that every time you need some work done, you have to fetch the data from the memory, and then you have to process it. But because of the fact that they're not together, again, it's the traveling time, right? You get the data, and then you process it. You get the data, and then you process it. Well, getting the data or sending the data back, it takes time. Okay? So that's the problem with the von Neumann. Well, if you look at the right side, the bottom right side, the NC, the neuromorphic, is all intermixed. Okay, you don't have the CPU on one side and the memory on the other one. It's all combined all together. Okay, so that means that very near access to the memory. Okay, it's almost like in-memory computing. Okay, so just to repeat the difference, the von Neumann computer or the traditional architecture is that you have a separate processing and memory unit. Also, right now, the traditional computer is all binary. That means it's all 0 and 1, right? Okay, and then it has, because of the fact that they are decoupled, the speed takes longer time, okay, to fetch the data and then process it. And also, the energy that it takes is a lot. So it has a very high power, which means that it gets hot. So you probably look at it sometimes where you use the cell phone or use your PC, you feel like the heat, right? Because it cannot dissipate the heat. So that's the high energy problem. Okay, this is the traditional computer, von Neumann. Okay, so again, if you compare side by side, von Neumann, if you look at it, here's the CPU, central processing unit, and here's the memory unit. So they are separate. And then the data goes in between the processor and the memory. Okay, so input comes in, and then you have to go fetch the data, process it, and so on. And then finally outputs. Okay, in the neuromorphic, it's all intermixed. Okay, so in the von Neumann, the operation is called sequential. That means that you do one thing and then you do the next one. It's serial. Okay, while in the neuromorphic, it's in parallel processing. You can do things at the same time. Okay, so that's the difference between the serial and the parallel processing. Okay. Also, okay, we mentioned that most of the digital computers are binary, 0 or 1, right? In the neuromorphic, it's more like analog. Okay, it's not just digital, 0 and 1, but it's actually many values. Okay, and the R1 is that in the von Neumann is a binary data, while in the neuromorphic is spike driven or event driven. What is an event driven? That means that you send a stimulus. Whenever you receive the stimulus, then you do something. If you don't receive the stimulus, it's event free. That means so whenever it's not doing anything, it's dormant. So that means it does not consume power. While the other one is continually consuming power because it's always on. While in the event-driven one, if it's not moving, you're not consuming power. So that's called event-driven. Is that whenever there's a stimulus, then you activate and you do something. But if there's not a stimulus, you don't do anything. Okay, that's the difference. Okay, so let's summarize in one slide. What are some of the characteristics of neuromorphic computers? Okay, first of all, the processor and the memory is together in one place. That's co-located. Okay, both. They are not split. They are parallel processes. That means that you can do many things simultaneously. It's not sequential. Okay, it's event-driven. That means that when there's no activity, you're not wasting power. Okay, that's what event-driven means. It is highly adaptable and it's plastic and it's flexible. Okay, it's also scalable. It can size large or size small, size large or size small. Okay, and fault tolerant, that means that if some part of the machine is wrong, you have a backup. That's what fault tolerant means. All right. Yeah, you have a question? FAT? Excuse me? FST? Oh, full self-driving. Okay. Yeah, we'll talk about applications a little bit later. Okay, so let's leave all the questions till the end. Okay, but let me just explain all the basics and how the thing works. Later on, we can talk about any applications you want. Okay, in terms of driving and all these other machines. Okay, so if you look at this slide, sort of like summarizes the features of neuromorphic computing. Okay, if you look at the bottom, it has 4 blocks. Okay, massively parallel. That means that you can do many things simultaneously because it's not sequential. In a sequential approach, you have to wait till the previous one finishes, then you do the next one. So that's a serial or sequential approach. Parallel means that you can do things at the same time. Okay, you can work on many things at the same time. That means why it's so fast. Okay, instead of doing one thing at a time and you have to wait for the previous one to complete, you can work on many things in parallel. Okay, that's why the speed. Okay, we mentioned that the memory and the processor is collocated. That means that you don't need to go and fetch the data from before the processor can act upon it. Okay, so it's located low power. Okay, that's one thing that right now, if you look at most of the mobile devices, whether it's the cell phone or whatever, is that you don't want to burn your hand, right? Because sometimes it overheats. Like for instance, I think one of the cell phones that came up, I don't know which generation came up. People say, well, I'm holding it in my hand, you can feel the heat, right? That means that the heat is not dissipated, okay? Because the power is so high. And the other one is event-driven. That means that it's not doing anything if there's no activity. That's event-driven. Event-driven was a term that people like in my world, I was in EDA. When we say event-driven simulation, that means that if there's a stimulus, we do something. But if there's no stimulus, you don't do anything. That's event-driven. While the other one is always on. That's why it's hot. Okay, so let's go over one by one some of these characteristics for NC. I'm just going to use NC for neuromorphic computing, okay? So we already went through the way that it's inspired by the human brain. So inspired by biology, okay? The way that neurons work, that's the way we're going to make NC work. Okay, so again, it's the picture of a neuron interacting with another neuron or many other neurons, and the way you interact is via synapses. That means that there's a stimulus that happens, and it passes on to the next one. It's not one-to-one, by the way. It could be one-to-many, right? So one cell could be interacting with many cells. Because in our brain, you have many cells, all neighbors. Okay, remember the picture that I showed you where everything is intermixed? Okay. Okay, so that's one. Second one, event-driven. There's the NC is based on spiky neural networks. The neural networks is the one that I just showed you, the perceptron, where you have multiple inputs coming to a hub, and then you do something, you multiply by weight, you do something, you sum it together, and you send out as an output. Okay, that's the perceptron. So this is the perceptron. At the bottom of the slide is the perceptron. Inputs, and then the sigma sign is you sum it up, okay? And then you apply a filter. On the right side of the circle, you have a thing. Here is you apply some filtering, and then you have the output. Now, if you notice, you see some small bars here in the input. That means that's event-driven or stimulus-driven. If you have a stimulus from a previous neuron that comes to this neuron, they say, oh, I detect the activity, so I'm going to do something about it. Okay. Energy efficiency, I think I already explained that. Real-time processing, that means that whenever you feel or do, you react immediately. That's real time. Okay. So if I throw a ball to you, you immediately catch it. That's real time. Okay. If you go and say, okay, let me throw, but you have to bounce the ball somewhere else before you get it. That's not real time. So whenever people talk about cloud versus edge, cloud means that you have to go through a server to get it. The data is residing in the cloud. Okay. The edge means that you are right next to the device where it's happening. Well, that one is a separate thing. End-to-end means that you interaction between one-to-one or one-to-many or many-to-many. That's what you are talking about. No, here real-time means that it happens right away. Right, that means. So end-to-end, it means that the number of elements that you're interacting. This one is the speed that is interacting. The real time means that I tell you, you hear my voice, you do something right away. Okay, stand up when you stand up. Okay, that's real time. The one-to-n or end-to-end means that if I'm telling everybody in the room, okay, stand up, that's a one-to-n, right? If you say everybody to everybody, it's end-to-end. Okay, so that's one is related to the number. The other one is that how fast you react. It's two separate things, okay? Okay, now, everybody knows that a computer is made out of two things. One is the software and one is the hardware. The hardware is what you see, the computer, the PC, the cell phone, right? And inside there is all software, okay? So one of the things that I'm not going to spend a lot of time today, but for people who are electrical engineers, okay, when we took our electrical engineering course, you probably remember the three linear passive elements: resistor, capacitor, and inductor. Okay, so I'm not going to go over the whole EE curriculum tonight. So, but one of the things that is key to neuromorphic computing is called the memristor. The memristor is like combining two words, a resistor with memory. So that's called a memristor. Okay. Now I'm just going to show a picture here. So for people who are not EEs, don't worry. You have resistor, capacitor, and inductor. Okay. Because in electrical engineering, you have a current, you have voltage, and you have a flux, and you have a charge. Okay. So there's a interaction between those. Okay. So dq dt, the change of rate of the charge with respect to time, that's the current. Okay. The voltage divided by the current, that's the resistance. Okay. So anyway, I'm not going to go into that, but I just mentioned that because of the NC, now they introduce a new element called the memristor. Okay, memristor. That means a resistor with memory. Mem is the memory, resistor for resistor. Okay, so this one in red is called the new element. Usually in EE, you just have ROC, resistor, capacitor, inductor, right? So now there's a new thing. And why do you need a memristor? Remember that I mentioned one of the characteristics and features of the NC is that the memory and the processor are co-located. So if you have a resistor, you need something that also can remember. You can remember the previous state. So as long as you don't change it, you'll keep remembering that state. So that's what the function of the memristor. So that's to the amount that I'm going to go over with this audience, okay? Okay, and then there's some other ones, like the Hebbian learning, okay? I'm going to just mention it to you so that when you go out after this seminar, you can be dangerous enough to say, oh, I learned from Bill today about Hebbian learning. You know, people say, what is Hebbian learning? Okay. Okay, Hebbian learning is like, remember that the neurons are cells. Okay, so cells that fire together. That means fire means you send the stimulus. That means fire. Okay, then wire together. It's almost like among friends. If we do things together, then we become friends. Then you have common activity. Okay. So heavy on learning, that means that remember that whenever a neuron sends a signal, it can affect many neurons nearby. Okay. So the more they interact with each other, the closer they are. Okay. And the strength of the interaction is stronger because you have multiple stimulus coming into play. Okay, that's what in a nutshell was heavy on learning. Heavy on learning means that when it's more than one person telling you what to do, you have multiple persons telling you what to do, then the effect gets compounded. That's what the way I would explain what heavy on learning means. Okay, now in the past, when we talk about AI, there's a supervised learning. Is that when the human supervises the machine, and there's an unsupervised learning. Okay, so we're diverging a little into some of the previous seminars where I talk about the different modes of learning that the machine does, machine learning. Okay, another one is called reinforcement learning. Reinforcement learning means that you learn it and then you relearn it again. You keep repeated learning. That's called reinforcement learning. Okay, so all of that is part of machine learning. So as a matter of fact, you can go online, you can get a degree from Stanford or from MIT if you want to know all the stuff, the in and outs of machine learning. But throughout some of the seminars that I'm giving, at least you have heard about some of the terms. You heard, oh, yeah, Bill talked about supervised learning and unsupervised learning. Okay, the supervisor is the human. Okay, so if the person tells the machine, this is an apple and this is an orange, you're supervising the classification. If you don't do it, the machine does it by itself, it's unsupervised. Okay, reinforcement learning means that you keep doing it. So the more you do it, the more often you do it, the more ingrained it is in your knowledge. Okay, by the way, I'm teaching AI. You know, the way that I learn things today, I actually imitate the machine learning method. That's the way I learn. First of all, I try if for instance, if I view a YouTube video on neuromorphic computing, and then I view the whole YouTube, I understand only 50% of it. What do? I go and watch our YouTube on neuromorphic computing. If I don't understand, I watch the third one, the fourth one, the fifth one, the sixth one, any number until I get it. Okay. So that is the way the machine learns. And that's the way that I'm learning right now. So before, when we used to be software programmers, we would tell the machine what to do. Now I look at the way the machine learns and say, that's the way I'm learning. I keep going and learn something. If I don't get it the first time, do it in n steps. You may get it the third time, or you may get it until the 15th time. It really depends on you, but you keep doing it until you finally learn. Okay, that's called reinforcement learning. Okay. Okay, now there are other concepts about NC, hierarchy and parallel. We already explained what's the parallel processing versus sequential or serial, right? The other one is hierarchical. Every time you have an organization, yeah, people say, well, is it top down or is it bottom up? That means hierarchy, okay? That means that there are many layers, many levels. Okay, that's hierarchical. Okay. The other thing we mentioned repeatedly is that everybody right now worry about energy efficiency. So we keep talking about NVIDIA's GPUs, and they consume a lot of power. They get very hot. Okay, so people say, well, you know, a data center consumes as much power or utility as a city. Because all the machine learning, all the AI, it takes hundreds, thousands of GPUs. So we were talking about NVIDIA H100 or A100, okay? It takes thousands and sometimes 10,000, 100,000 of those GPUs. And imagine the amount of power. It's very hot in the data center. Okay. So just to digress a little bit. So right now I'm doing very well in terms of time. So let's give a little bit of background about how NC has evolved. Okay. I mentioned at the beginning, remember the circle input with a lot of inputs, x1 through xn, multiply by the weights, and then you sum it up, and then you apply a filter. Okay, that's a perceptron. That's the mathematical model. And that was developed in the 1950s. Okay, actually, it says US Navy created this mathematical model called the perceptron. That was the beginning of it. Because if you look at, remember that I say, well, this is the biological brain and here's the artificial brain. They all use the neural networks and the perceptrons as a unit, okay? So that perceptron was actually developed in the 1950s. That was the beginning of it. The second item goes back a little bit to the days when I was in school. There's a very famous professor from Caltech called Carver Mead. He wrote a book called VLSI Design. That was one of the most famous books. Huh? VLSI Design. So it's a book that teaches people how to design an IC chip. Okay, VLSI Design. VLSI stands for very large scale integration. The VLSI was a term, just like everybody says, well, what is FBI? What's CIA? Okay, the US is enamored with acronyms, right? Yeah. So VLSI was a term back in the days when the chips were getting smaller and smaller and the number of transistors were getting larger and larger. So it started with SSI, MSI, LSI. SSI is small scale integration. MSI is medium scale integration. Large scale integration. VLSI is a very large scale integration. Okay. And then later on, you went to, I think, ULSI and so on. Okay. So anyway, in the 1980s, this is a famous professor, Carver Mead. Actually, I have a copy of that book because that was back in the 1970s, late 70s. So that's as old as I get. Okay. So I actually had a copy of that book. Now in 2012, so in between, there was nothing happened for many, many years. Okay. In 2012, there's a project in Europe called the HBP, Human Brain Project. Okay, remember that we're trying to learn more about the human brain. Okay, so that was a research that was done in a conglomerate from Europe that was working on this called the Human Brain Project in 2012. And then later on, I'm going to talk about two companies who have already developed NC chips, neuromorphic chips. One is IBM and one is Intel. Okay. So IBM developed in 2014. So that's only 10 years ago. So all this technology is still pretty new right now. Okay. Intel developed in 2017 and 2021. So 2021 is only 3 years ago. Okay. Okay, so I'm going to go over what some of this development at IBM and Intel. So the IBM project was called True North. True North. Okay. And the Intel was called Loihi. I don't know, some people pronounce it Loihi, but it's actually nothing to do with Hawaii. Okay. So it's a Loihi. So let's go over. Remember that, so these are two major companies, IBM and Intel. IBM in 2014, they developed a project called True North. Okay. And they developed a neuromorphic processor. And at that time, it had, okay, actually it says 1 million neurons. Remember that the human brain, how many billions of neurons do we have? 100 billion, about 100 billion neurons. So the way that IBM did it for that project started with about 1 million. Okay, but it was very low power. So it was on 70 milliwatts of power. Okay, so this was the chip that was developed 10 years ago at IBM. True North. Okay. 1 million neurons, 256 million synapses, 5.4 billion transistors, and only 73 milliwatts. That's actually pretty good. You know that the human brain, it consumes only 20 watts. You know that when at home, when we go and change the light bulb, okay, like at my home, most of my light bulbs are 100 watts. Okay, well, the human brain, only 20 watts for the whole brain. And it's how many billions of neurons? Okay. Okay, so that was in 2014. So that was 1 million neurons. And what is their target goal? Every time you increase it by millions, or 1 to 2 orders of magnitude. So you start with, say, 1 million, next time is 10 million, 100 million. So you keep raising the order of power of 10. Okay, and then one day maybe they'll get to billion transistors, billion neurons. Okay, so that's even on linear scale, it's going to take many years. Okay, Intel came out with 2 efforts, one in 2017 and one in 2021. Okay, so they started with initially only 130,000 neurons. And in 2021, they came out with 1 million. So Intel effort, just comparing the two companies, Intel is way behind IBM, right? Because the IBM did the 1 million in 2014. Intel did 1 million only in 2021, only about 3 years ago. Okay. Okay, so these are the chips. All these are real chips. They are already out there. As a matter of fact, a lot of these chips are already being used right now for different applications. But between Loihi 1 and Loihi 2, there's a lot of improvements, speed improvements, and efficiency improvements. Okay, so now let's digress a little bit and talk about what are the uses of NC. Okay. By the way, on today is September 11th. On September 21st, that's a Saturday, I'm giving a keynote on an AI conference. It's called AI applications. It's the applications of AI in 10 different domains, from education to transportation, okay, to all the biotech, all different kind of transportation, biotech, education, and so on. Okay, so that's Saturday, September 21st, from 1 to 5 is a conference. So it's called AI Now and the Future, something like that. Huh? You probably heard about it, huh? Where? It's in Fremont. There's a company called Delco Electronics. The company is called Delco. Delco used to manufacture car parts. In the car, there's like car parts. Delco Electronics is a very famous electronics company. So it's located on Fremont Boulevard in Fremont. On 880 is the Fremont Boulevard exit. Huh? No, No, it's not Teradyne. No.
Yeah.
Well, anyway, it's Delco Electronics. Okay, I'll show you the slide at the end. Okay, so for people who are interested in attending. Okay, so let's talk about NC applications for a while. So I'm just listing some of the top 10. Okay, there could be any, just like when I talk about AI applications, there are so many. Almost any domain people want to use AI, right? These days, right? So neuromorphic computing applications. One is edge computing and IoT devices. Remember the comment I was making is that, for instance, if you have a driverless car, the car is the edge, is the device. And you want instantaneous response, real-time response. Okay, that's edge computing. So you're not relying on the cloud because the cloud takes too long response time. IoT, Internet of Things. Okay, so every small thing is called a IoT. From the cell phone to a thermostat to a refrigerator to an animal like a cow, they're all a thing. Okay, it started with Internet of People. Okay, and then it started with things. Okay, so edge computing, IoT, real-time processing, also robotics. By the way, that's another theme that I'll be covering in the Night 21. I'm covering AI applications and also specifically AI applications to robots. Okay, even more specifically to humanoid robots. Okay, so robotics is an application of neuromorphic. Healthcare. That's going to be the first application of robots, by the way. It's going to be healthcare, domestic. There are three areas for AI right now, or for robots. One is healthcare, taking care of the elderly, right? And patients that need assistance. The other one is that what they call domestic robots, the help that you need at home, vacuuming, doing the dishes, preparing meals, helping elder people get up, that's domestic. And the third one is called industrial, like the robots that Tesla uses to manufacture the EVs. Okay. Okay, the other application is AI in general. Because we think the robots, now the difference with today's robots from the old time robots, before the old robots, they were not necessarily like human-like. They were just like an arm that help assemble some part of in the factory. Okay, now it's more like human. It has a leg, it has a head. Okay, even has a human, or who has AI or ChatGPT inside the robot. Okay. So what's the benefit of having the robot with the brain? Is that you can communicate directly with the robot. Before, the robots used to be, you have to program the robot to do certain things, a fixed function. Now you can talk to the robot and the robot would understand you and say, oh, you want me to grab the apple from the table and put it in the pocket. Okay. The robot, if he has ChatGPT, will be able to understand you. And you can communicate with it via voice. Before, you have to program it. You have to write the instruction. Security and surveillance, that's another thing. So anything that we talked about earlier about neuromorphic, that means using neurons. Neurons is the cells that there are cells in your eyes that can see things. There are also cells in your ear that can help you hear things. Okay. So anything that has a sensory function, seeing, hearing, touching, smelling, tasting, okay, all of that, you can apply neuromorphic computing because it helps you in the sensory aspect of it. Okay, we also already talked about autonomous vehicles. You need to have I don't know, 5G is not here yet. I mean, 5G is not fast enough right now. So that's why, you know, that driverless cars, people have been talking about driverless cars for at least 3 to 4 years. And people are always waiting, and still it's not out yet, right? Because there are still technical difficulties that have not been solved. We can discuss that, you know, later on. Okay, so autonomous vehicles. Right now, anything that has a autonomous car, it has sensors around the car. You can catch things, view things. You have cameras. You have LiDAR. Okay, you have sensors around all sides of your car. And then also how to avoid collision. Okay, so all of that are applications. Security and surveillance, that means that you can, you know, something equivalent to the night watchman, right? You can look at it and you can see things. Okay, applications like adaptive control system. That means that things that are being used in industry. And for instance, you have to assemble a car. Okay, so you can do that. Also, smart grid, that means energy. Utilities, you can use that. Cybersecurity. Environmental monitoring, so that means like clean technology. Okay, the environment, green energy. And also, last but not least, gaming. So in order to make things more real, you can use neuromorphic. Okay, because it's going to be behaving. It's going to be able to adapt to things just like humans. So the more it is like human, the more real your game is going to be, right? Because it's almost like, oh, okay, the game can understand you. Okay. Okay, so we're doing very well right now. We should be wrapping up by 8 o'clock, and then we're opening up for any Q&A. Okay, so what are some of the challenges? First of all, I mentioned that this is a technology. If you look at even the products that have already been out, like IBM and Intel, it's all within the last 10 years. So, and it's not proliferated yet. So it's basically still testing. As I mentioned, we're still like 1 million neurons. And we have 1 billion neurons in the body. Okay, so there's still scaling still has about 3 or 4 orders of magnitude away. Okay, so what are some of the challenges for neuromorphic computing moving forward? So the title of tonight's talk was called Neuromorphic Computing, the next evolution of AI. That means that's the next step. That's where all the trends and the investigation is moving toward. Okay, but we're definitely not there yet. I mean, we're just at the beginning. It's the first step. So the baby maybe has been born, but it doesn't know how to walk yet. Okay, it's still in the crawling. So accuracy is still not there. There are very limited software, and therefore it's not open for mass consumption, because it's not open for people who are non-experts. So if you don't work for IBM or Intel, where can you get your NC, neuromorphic computer? It's not available yet. Okay, so inaccessible. The other thing is that in order to test where you are at, you need to be able to measure. Okay, so that's benchmarking. If you have a benchmark, this is what it does, and then this is how fast or how slow it does it, then you can make improvements. So you cannot improve on it, anything that you cannot measure. So first you need to be able to measure where you are at, then you can improve it. Okay, so all these are challenges for neuromorphic computing. So in tonight's seminar, we talk about several things. We talk about the limitations of the von Neumann architecture and why people are going towards NC. Okay, we mentioned already. very high power, still not fast enough, it's not adaptable, does not scale. The CPU and the memory are separate and so on. They're all the limitations of the current computers. So people say, well, why don't we try to imitate the human brain? And that's the way that it got started, is that we're going toward NC, okay? But in order to move forward, the other thing is that we talk about the difference between the von Neumann architecture and the NC architecture. It's not going to, the NC is going to suddenly replace the von Neumann overnight. Most of the way that technology progresses is that they coexist at the beginning, okay? So you say, okay, well, von Neumann has its limitations, but it's still good for certain applications. And then you have limitations of the current architecture. Let's make improvements with the NC. And initially, both are going to coexist, okay? Just like any technology that you can face today, they will run in parallel for a period of time before one eventually takes over the old technology. So neuromorphic computing is just a newborn baby, okay? It has a lot of promises, and there's a lot of need for that type of computing technology, but the challenges are still many out there, okay? But in order to move AI to the next level, you need to improve all aspects of it. And NC is one of the ways that people are trying to say, okay, maybe we ought to move in that direction, okay? Because after all, AI is trying to imitate the human brain. So the more we understand how the human brain works and try to imitate it, not to say that that would be the final solution. Nobody knows how we're going to get to AGI, okay, artificial general intelligence, but that's certainly one of the ways that people are approaching, okay? All right, so that's the talk. Exactly, it ends at 8 o'clock. Okay, so just a commercial, a couple of commercials. Okay. I'm giving this talk September 11. I have one more seminar to go for what we call the fall series, okay, in the fall. Fall starts in September, October, and so on, the last quarter. So in October, this is my next talk. It's called 2024 Emerging Technologies Hype Chart. Okay. Right now, I'm shooting for October 16th. But, you know, I need to make the reservation for the room and so on and so forth. Okay. So just a couple of words about what this topic is about. Okay. Every year, there's a company called Gartner Research. They do a survey of the whole industry, of every industry, all the technologies, and they come out with the top 25 technologies, okay, that are the most promising. And then they map it into a hype chart. So what is a hype chart? The hype chart, that's what the way it looks. It has 5 phases. It's a technology trigger. That means like, oh, neuromorphic computing. Okay, people heard about the term, say, oh, people, let's start it. That's a trigger, okay, for a new technology, okay? Then it goes up to a peak of inflated expectations. Like for instance, right now, generative AI. Everybody heard about generative AI, ChatGPT, okay? Right now, that's the, I would say that's the peak of the inflated expectation. People expect a lot of ChatGPT. Okay, right now there's already 4.0 now, okay? After a while, people say, oh, but it didn't really do all the things that they promised. So it comes down to the trough of disillusionment, okay? You're not satisfied with the way that it worked. And then people realize, okay, maybe the reason why it didn't meet my expectations because I was not using it the right way. Okay. So slope of enlightenment, that means, oh, maybe still that's a lot of good, but I need to know how to use it in the right way. So that's the slope. So it goes up again, slope of enlightenment. and then finally it plateaus. Okay, in electrical engineering, it's called the steady state. You have transient and then steady state. Steady state means that you have reached the final plateau. So every year, as I said, Gartner does research so just came out in August. So we're right now, what, September? So it just came out last month. This is 2024 technology hype chart. So I'll be going over this hype chart, map the top 25 technologies into where it is in the trigger, in the peak, in the fall down, and so on. Okay, so this is what I'll be talking. So this is very hard to read because it's too small. So I sort of like summarize it in one slide. So see where you are interested in coming to hear about the following technologies. So for 2024, Gartner grouped into 4 major themes. Autonomous AI, that means AI, just like generative AI and so on, but it's more automatic. Okay, autonomous means just like self-driving. That's autonomous. The second one is called improve the productivity. The third one is user experience. The experience is the user, the way user just does it, the customer does it, and so on. There are many types of experience. Okay, you heard about virtual reality, augmented reality, all those are experiences. And the perennial concern about security and privacy. Okay, those are the 4 major things. And then all the 25 technologies will be mapped into these 4 areas. Okay, so I didn't list all the 25 technologies, but if there are enough technologies that from the list that you're interested, then come in October. Okay, so we talk about humanoid robots, reinforcement learning, generative AI is already at its peak. Okay, and then you have prompt engineering. That's another thing that people need to master, is that how to do the prompt engineering correctly. Digital twin, spatial computing. Okay, that's a new one, spatial computing. Digital immune system, disinformation security. Everybody is worried about the upcoming election, right? Federated learning, homomorphic encryption. Okay, so instead of neuromorphic, it's going to be homomorphic. Homomorphic has different meaning. It means something similar to it. Okay, so anyway, that is the October seminar. Okay, it's the 2024 Emerging Technology Hype Chart. Okay, I mentioned a little bit about the 921. So I'll be giving a keynote speech at this conference called AI Now and Future. Okay, it's organized by SVCACA, Silicon Valley Chinese American Computing Association. That's what SVCACA is. So I'll be talking about AI applications, okay, applications of AI in the various domains. And then, so that conference is called AI Now and Future. And then the other topic I'll be covering is AI in robotics. Okay, so if you're interested, that's September 21st. It's a Saturday. It's from 1 to 5. So you have lunch and then you go to listen. And hopefully you won't fall asleep. But otherwise, if you fall asleep, it's also good. Okay, so that's my next 2 events that I'll be participating. One is the seminar in October, and then this one is just in 10 days. So today's the 11th, and the 21st I'll be talking about that. All right, so that's it. Now open up for any questions. Yes.
Why IBM is not now the application is given to it.
Are you talking about IBM in general or IBM in neuromorphic computing? Because, okay, so
IBM in the morphic computing, neuromorphic computing, the synapse
Right.
is the one using it.
well, because right now, right now, actually, it's hard to say whether they are popular or not because there's very little exposure outside of IBM. All the people who have access, just like in AI in general, AI has remember the Watson,
Yeah.
IBM Watson. Supposedly, yeah, they're also doing a lot of work on quantum computing also, right?
Yeah.
So they have a lot of money, so they do a lot of R&D.
But
Okay,
now it's in general, like the kernel, like the OpenAI, the ChatGPT, or for the last thing.
correct.
It's a-
So
it's a
so
general
IBM
application.
is more, IBM. Well, way back when I was working, used to work for Xerox. So IBM was like our competitor. There's like the big companies like IBM and Xerox and AT&T, all the big companies, right? Now, at that time, everything was not open like right now. Right now, everybody said, okay, let's do open source. Everything, let's make it available. So a lot of the companies like what IBM Watson, IBM had a program that beat remember the show that had to be able to answer the questions very fast. The other machine that beat the chess player. All of that, but was not really available. Right now, they're beginning to open up a little bit, say, well, we have quantum computer, we have this other neuromorphic stuff.
So IBM try to promote the synapse people also they have the semiconductor, they also show demo. But the reason I believe the reason is not popular is because of they need the application, right? They cannot be used in general. So that's my question is that neuromorphic computing is also just some spatial activity. Even quantum computing maybe also just used to some very spatial application is very
Okay.
powerful.
So the answer is yes. It's very limited because of two reasons. One is because the capacity is not there yet. Right now, we're still having like 1 million neurons, where we have long ways to go to billions, right? So
if that's the reason, if you can scale out or scale up to the
well, that's the mentality about open source and so on. To say, if you make it available to everybody, then maybe you'll move faster, right? And have different times, So, so that was one limitation is that it's just beginning. So it's like a baby doesn't know how to run it because it can barely. Right now, it's just crawling, right? And also, it's not available to everybody. So that's the way that IBM, Google is the same. A lot of the things that they do is not like open for everybody.
What do you think the Tesla? So, computing.
Well, Tesla is not available for everybody either, but Tesla is smart because right now they're leveraging, for instance, they started with the EV,
Yeah,
right?
Exactly.
And they say, well, we're going to have the EV that's going to also have software that navigates.
Yeah, they
by
have
itself.
millions.
Right. And now I bet that actually within a year or two, Tesla is going to be selling robots more than selling EVs. Mark my words.
Yeah.
Okay. But they're like, for instance, even NVIDIA, why they're doing so well? It's because of their GPUs. But did they have the vision 10 years ago that the GPUs was going to take over the whole AI and so on? 10 years ago, people have not envisioned that AI was going to be smart.
Yeah.
Okay, so they lucked out. They developed GPUs, and the GPUs they found out that was not only for gaming, because they were using power processing and so on, but it was the gaming chip was also good for AI because they power processing. Okay, they did matrix manipulation. So they were lucky.
Imaging process.
Right. That was the original gaming was because it was done for the team playing electronic games. And they need 3D. Right. That's the way it started. And then when they halfway, they found out, oh, by the way, if you want to do AI, you also need the same type of hardware. So they were lucky. Well, Tesla started with EV. And now they say, well, we don't have enough manpower to build the EVs because now they're also coming out from the China market. So they're going to go somewhere else. They say, well, where are the workers? So what Elon Musk is going to do is going to fabricate all robots. And then all the factories, Tesla factories, are going to be manned by robots.
And also robot taxi.
Correct. So once they develop the robots, they say, well, we're going to use the robots not only to assemble cars, but we're also going to sell the robots for the families who need, and we're going to, that's why I said the top 3 applications of robots. The one that in the factory is called the industrial robots, right? The second one is called domestic robots. Like originally when the things came out for the house, you have the Roomba, the vacuum cleaning inside the house, right? And then they have the robot dog that will pretend to be a dog inside the house. All of that's going to be taken over by domestic robots. So a robot that is being used inside the home, that's called a domestic robot. Okay. And the third one is in healthcare. All the elderly people, also the hospitals, all these other ones to take care of that. Those are the top 3 uses of robots. So, but again, Tesla is going to be lucky just like NVIDIA. They say, well, we're going to develop the Optimus to use in the Tesla factory. But I bet eventually they're going to sell more robots for domestic use and for more than just. There are many, by the way, I don't know, I didn't prepare for tonight's talk to talk about robots. But there are many companies who are working on healthcare robots. There are 1 or 2 that were designed specifically for healthcare. A couple of them are from China. Okay. Now, the other ones, like for instance, the OpenAI also developed a robot through another company, right? OpenAI, Amazon, and so on, they're all going to say, okay, we're going to go with this company who's manufacturing robots. And everybody's going to use the robots for different purposes. But there are companies, a couple of companies that their initial intent was to help take care of people. Actually, I have the information. So see, if you send me the email, I'll find it out and send it to you. But I don't have it right now on the top of my head. Actually, I may have it if I can find my robot presentation. Because actually I talk about more than 20 robots in my past talk. Otherwise, come to the September 21st. But the easiest way, send me an email, I'll tell you what company is doing the healthcare robots. Okay. My email is B as in Bill, BKAO. KO is my last name. B Kao, Bill Kao, 2K, because I set up that email account in the year 2000. So B Kao 2K, I'll be a good guy. Send me an email. Send me a question or what you are interested in, and I'll reply just like ChatGPT. You ask me a question, and I'll answer. All right. So anything that I cannot answer tonight because I didn't have it in my presentation, but if you send me an email, I'll be glad to answer. So there are companies who are already working on healthcare. There are also a couple other companies who have robots working for car assembly, doing Mercedes, also doing Japanese car company. So those robots is just to help in assembling the cars. Oh, let me come back to just in case there are still people watching the Zoom, because I was wondering. Okay, so just to summarize what I was talking to some of the in-person audience is that people were inquiring about healthcare robots. And then I was saying that the top 3 applications for robots are going to be healthcare, domestic use, and industrial robots. And then I'll be covering specifically use of AI for robots on September 21st. Okay, any other general questions on NC or any other topic? I'm ChatGPT, so you can ask me anything. If I know the answer, I'll answer.
So AGI will work or no?
What?
AGI.
AGI? Okay. So let me say a few words about AGI. That's a very common question about AI. So right now, everybody knows that there are many kinds of AI. The one that we started with is called narrow AI. Remember the AI that beat the chess player, the chess champion, and then they have a AI that beat the Go champion. Okay, all the AI used to be very narrow. It does one thing better than humans, but it does only that thing. So the AI that beat the Go champion cannot do the vacuum cleaner or cannot cook you a dish, right? Because it's not general. We humans, you know, we can do a lot of things. We have to go to the kitchen and prepare a meal. We have to also go and prepare the tax return. We have to also go and pump the gas in the car. We have to also do dishwashing, washing the clothes, everything, right? So that's general, okay? So the way that ChatGPT started, why was ChatGPT so hot? Because before, all the AI used to be, that's one thing only. But when ChatGPT came out, everybody, no matter what, you could be in the finance, or you could be in some other area, you ask the question, the thing will have an answer. It's just sort of like a smarter Wikipedia. Wikipedia had a lot of answers for many things, right? So ChatGPT also had answers for many, many different areas. So people say, oh, wow, I have something that can help me get the answer instead of doing a Google search. 2 things that ChatGPT, when it came out, did better than before. Before, it was a Google search. That means you have a question, you ask Google, and Google will give you 20 links, but you have to go and read it yourself. And you don't know which one was good, which one was bad. So that was the old model, the Google search. Okay. ChatGPT, you can ask directly. Okay. Prepare me a slide on this. You will go ahead and do it. That's actually the power of generative AI. Okay. Before, the AI and so on was just an answer, but you not create something. The generative AI that is much better than before is that now it can create something from nothing. You can ask ChatGPT or some of the image creators, say, draw me a horse galloping on the moon. Can you find from the previous drawings, no matter up to all the art that you have seen up to now, anybody draw a horse running around on the moon? No. But now if you ask ChatGPT, it can create a horse just actually running on the moon. So that's creating something that did not exist before. That's called generative AI. You can create from that something that did not exist before. So that was also a big improvement over the past. Okay. But so let me come back to your original question about AGI. AGI is going to be a few years away because the technology to get to AGI, I don't think it's there yet. So there are a lot of experts on AI that they say that the LLM is not really the right way to get to AGI. LLM is a text-based, is a language-based solution. But right now people say, well, how did the cat learn when the cat jumped from the table to the floor? The cat didn't learn language. Also, the kid that has not gone to elementary school yet, he has never received any schooling. But when the kid looks at things, he said, oh, you know, this animal, the cat, is different than the dog. Okay. So it's not based on language. That's my point. So they say that LLM is not enough to get us to AGI. Okay. AGI is artificial general intelligence. Right now is narrow AI. It's very narrow. That means it cannot do general everything. Okay. Another observation related to AGI. We don't really need a AGI. If you look at today's society right now, AI is trying to imitate man, right? Artificial intelligence is trying to imitate the human brain. But do you know that right now, is there a person in the world who is the best scientist and who is also the best athlete and also the best musician and also the best gardener and the best cook? No. There's experts. So right now, as I mentioned, the three top categories for robots: domestic, healthcare, and industrial. Okay, each one has a different need. The one that assembles car for Tesla doesn't need to know how to get the man to Mars. He doesn't need to know space travel. He doesn't need how to land the rocket on the moon. Okay. The robot that takes care of an elderly, maybe he needs to know a little bit more about biology, medicine, and how human, you know, does things. But that person doesn't need to know how to assemble a Tesla EV. The point is that there's really no need for a general purpose that can do anything. Why? Because even if you look at us, okay, we can drive a car, we can balance the checkbook, we can go and buy groceries. But can you land a rocket on the moon? You don't know all the equations that are applicable to gravity and how to, you know, how much how do you manipulate the rocket in space? You don't know that. So the point is that there's also no need for us to know everything, right? Because each of us, we only need to deal with our own environment. So if I don't need to land the rocket on the moon, I don't need to know, you know, all the equations that are, you know, second and third order integral differential equations, because I don't need to. Okay, but if I'm a sports person and I say, okay, how do I swing faster? Okay, he needs to know only that. Okay, a person who knows how to play the piano and the violin, he's not necessarily the best basketball player. Because different people have different needs. And you don't need to have a Superman that does everything. Because even in our, and think about it. So that's the way that you need to think. A robot or AI is a helper, is an assistant to a person. So while you don't need to have a robot to help you. But let's say that, you know, my eyesight is getting worse. So I say, well, I need a robot that can drive a car on that. Okay, so that's my need. Okay, but it may not be your need. You say, well, I'm still young, you know, I have 20/20 vision. So I don't. So it's different. And if you think about it, why I'm making all these comments is because right now the LLM approach, now it takes longer and longer to train the model, right? Okay, so now with 4.0, and then now it's going to come 5.0. Okay, now it's taking 1 year to train the AI model. But do you need the AI model to know English and Chinese literature and Japanese literature and everything else and Latin? No, probably not. If you're living in China, you have the robot that is very well versed in Chinese poetry. Okay, but doesn't need to know Spanish. Okay, so the point is that if there's not a need for everything under the sun, you don't need to train a large LLM that. The way I envision the things is that everything will be domain specific. So if you go into the medical field, you need to know everything related to medicine. But you don't need to know everything how to build a plane. Okay? And if you compartmentalize the need, you don't need a very large LLM. My point is that you make it into domains. And if you want to train a robot or an AI brain that knows everything about medicine, it's different than if you want to have an AI that knows medicine and music and art and whatever, all the languages and whatever. It's no need. So that's the way I envision that AI is going to be going, is that people are going to realize is that you don't need to have a large language model that knows everything under the sun. Okay, you tell me what you need, and then you just train the robot or the AI to do those things that you have checked. Okay, but you don't need to have everything. Yes, but I would still say that the robot, you group it into function. So that's why I say there's a domestic robot that knows how to do all the chores around the home. Okay, plumbing, electricity, cooking, meals, whatever. That's all related to your house, right? What you need in your house. That's already multiple function, because right now today, the person who comes and fixes your plumbing is different than the person who comes and paints your house. But you can have a domestic robot that can know all of that part, group it all of the needs into one robot. You don't need to have multiple robots. Okay, one robot to paint the house, another robot to cook you a meal or whatever. You group it, but you can do multiple functions. That's the answer to your question. Quite easy. It's easy. I mean, right now the LLMs try to answer any question. If you ask ChatGPT any question, it can give you an answer. So right now, it already does more than what you need. And it knows a lot of things. Right now, the thing that we're missing right now is that make sure that the robots catch up with the brain, with the LLM. So let's say that you go and ask ChatGPT a question, it can give you an answer. But so you have only the brain, but you don't have the hands and you don't have the feet. So nobody can help you do the things that you want. You can only ask and you get the answer, but nobody will do it for you. So that will happen when robots come out. The robots are your arms, your hand, your feet, and your eye, your ears. Right now, the LLM is only your brain. I think that sort of summarizes the explanation. Okay. Well, again, I appreciate you coming to the seminar. Hopefully you learn something that you didn't know when you walk into the seminar room. And, you know, you already know also what's coming in terms of the October. So if those topics are of interest to you, then come and hear the October presentation. Okay. Okay, thank you. Thank you for the people attending tonight, as well as people via Zoom.
Are you going to put the slide
Slide of what?
those,
Oh, the which one?
like an event.
Oh, the one in the 921?
Yeah,
This one?
I think
This one.
I understand it.
This is September 21, 1 to 5.
I cannot confirm that, I'm referring to.
Yeah. Well, anyway.
October,
So I'm here just promoting two events. One, the October seminar, which will be October whatever 16, and then this one, which is September 21st. You know, if you cannot make it, then you cannot make it.
I mean, you had a room on the other side of the world. I went around and walked around for 1 hour.
Oh, before you came here?
Painful. So I mean, the basic might come and cell phone takes in. Go across the road, and I thought the cell phone is wrong, but apparently the cell phone is right.
Yeah. So anyway, for any future related to seminars from CIE is going to be here. So once you make it
So
today,
is this
next
going
time
to
is
be,
here.
is this going to, you're not going to move it?
No. No.
See, I mean,
But a lot of people, you know, I've been giving these seminars for 10 years. For the first 8